All right, so what is recursion?
When a method calls itself inside
Okay, when a method calls itself. Okay, it's recursion. Why is recursion memory inefficient?
Because the action stores the result and reduces the result when it calls itself.
So it keeps adding more and more data to memory without actually removing any.
Okay, which data is added to memory?
It would be like all of the old variables.
Okay, so you were kind of pointing out that sometimes we need to wait on one version of the method to finish before we can move on, right? So we got to put that on hold somewhere. So we have to store all that information related to a single call to that method into memory. We put it into something called a stack. I think last time didn't we show a stack overflow exception? All right, so it's memory inefficient because every single time you make a recursive call, you are pausing the current method and have to store all the variables associated with that somewhere. Okay, and that becomes very expensive in terms of memory. That doesn't mean that recursion is bad, because sometimes recursion is a very elegant way of solving a problem, and we're going to see that today as we continue on with merge sort. But we do have to consider the memory ramifications of recursion before we use it, okay, because it is important. All right. Oh, and I received bad news this morning. You guys didn't have a homework assignment? What's up with that? Did I forget to give you one?
No, you just said it was a beast of one and you didn't want to put it up yet.
Oh, but that would have been funny. How much of that was out loud? Does that make you feel good or bad?
That we don't have one homework assignment?
No, that I find your stress funny. That's a little messed up. All right, so let's go back and let's review this merge sort thing, since we were kind of going through it quickly at the end of class last time. But I'm going to start a second slide here that kind of gives us the pseudocode of the merge sort algorithm. All right, so we're going to be adding to this as we draw our pictures. So we're going to start off with a collection and just pretend like these are all, oh, here, we'll space them nicely. Perfect. All right, and this is, of course, to scale. So we start off, we have a collection of data that we would like to sort. Okay, in this case, we're going to store this in an array. All right, now, right off the bat, we're going to ask the generic question. Is this data sorted? And we talked last time that the only way at a glance to know for sure that data is sorted is if it's the one list. That is, it's a list of only one value. By definition, one value is already sorted within itself. Make sense? So the principle of merge sort is to continue to divide our list up, calling merge sort on the parts of the list. So we're going to divide it in half. Call merge sort in the first half, call merge sort in the second half. Divide the first half in half. Call merge sort in the first half, call merge sort in the second half. Divide the first half in half. Call merge sort in the first half, call merge sort in the second half. Until when we finally divide it down to something that only has a one list. At that point we can say, this part of it, this one little section of our list is sorted. Okay? Then when the other half, when we finally get down to the point where we can say that's sorted, we bounce back up and then we do the merge step, where we merge these two lists that are sorted within themselves. This list is sorted, this list is sorted. And we're going to go and merge these two into a single list that is sorted itself. That's the merge step. All right, so we're going to go ahead and split this up, and then we'll actually go through the merge step for one of these examples with variables. So right off the bat, we ask the question, is the current list sorted? The answer is no. So let's write that question down. no, split the list in half, call merge sort on each half. Now keep in mind, what does merge sort do? Merge sort sorts a list. Okay? So when we call merge sort on the first half, we're going to say only look at the list from bucket 0, only look at the array from bucket 0 to bucket 4, for example. And the other half will be look at bucket 5 all the way to the end. That's how we designate the halves. So we'll have to look at begin end for those guys. Okay, and we'll do that. We'll see that, the algorithm for it. So if the current list is not sorted, we will split the list in half, and then we'll call merge sort on each half. If the answer is yes, it is sorted, we are done.
Is merge sort a method that we're creating?
We're creating it. Yep. Just like we wrote bubble sort. So this is another sorting algorithm called merge sort. All right. So we're going to ask that initial question. Is this sorted? No, not the one list. So we're going to divide this in half. So we'll take the first, in this case, 5 buckets. There's 10 total buckets, right? So we'll take the length divided by 2. Take everything from 0 up to that point. So we'll make another call to merge sort, passing in only this part of the list. Okay? So this original call to merge sort was put on hold. That guy was put on hold while we made another call. Make sense? Then we asked the question. So again, algorithm for merge sort. Is the current list sorted? So we made a recursive call. We called merge sort again on that left half. So we put the current one on hold. Is the current list sorted? Is this guy sorted? How do you know? It's not the one list. So what are we going to do? When the answer is no, we split the list in half, call merge sort on each half. I keep wanting to think that the slides are, one's a slide and one's something else, but they're both slides. So we're going to split this in half. So let's just say the way we're doing our math is the bigger half always goes to the left. Okay? So we're going to split this in half, call merge sort on both halves. So we just put this call on hold. Now notice we haven't called merge sort on the second half yet because we're still working on the first half. There's 2 merge sort calls with merge sort. We call it on the left half, we call it on the right half. And we don't actually make the call to the right half until after the left half is done. Okay, we'll see this. So now we're looking at this. Is this sorted? No, not the one list. We'll split this in half. Oh my gosh. Okay. Is this guy sorted? No. Here, let's we'll create a second column. So this is column 2. Put a little divider. Look at my epic artistry. All right. So first call to merge sort, put it on a hold. Second call to merge sort, put it on hold. Third call to merge sort, put it on hold. Is this guy sorted? No. Split it in half. Call merge sort on the first half. Is this guy sorted? Yes. And what do we do when the answer is yes? We do nothing. We're done. So this particular call to merge sort ends. Then we call it on the right half. That's our second call to merge sort from that method, the one that was just put on hold. Now it's put on hold again. It was put on hold when we called merge sort in the left half, then left half ended, so we brought the other call back into existence. Then we immediately called merge sort again on the right half of that list. Okay? Putting it on hold again, we ask the question, is this the one list? It is. So what do we do if it's the one list? We're done. We do nothing. Now we're back up at this level. We are after our 2 calls to merge sort. We called merge sort in the left half. We called merge sort in the right half. So as of right now, what do I know? I know that the left half of this list is sorted within itself. And I know that the right half of this list is sorted within itself. So now I need to do the merge step. To merge these 2 sublists, I need to merge the left half and the right half into a single list with all the values sorted. Okay? So what we'll do for the merge step, here, let's what is it? Shift back. How do I go back? Shift tab. There we go. After both calls to merge sort are done for the left and right halves, we execute the merge step. So I'll create another slide. The merge algorithm, just the merge part of it. Create a pointer to the beginning of each half. Okay, so we're going to need 2 variables. One variable that marks the beginning of the left half of the list, and one variable that marks the beginning of the right half of the list. So we know where our lists begin. Because we know the left list is already sorted. We know the right list is already sorted. Now we need to merge those 2 together into one super list that's sorted within itself. And we're going to do that by merging. Okay, so let me actually, I'm going to take this guy. I'm going to create a new slide. And we'll do the merge step on this new slide. Okay? So we'll just bounce back here whenever we need to merge. So I'm going to create 2 variables. Let's call this left begin. And for right now, we'll do this with actual arrows. So left begin will be a 0. Right begin will be a 1 in this case. Because we have the left half is a 1 list, right? The right half is a 1 list. So each of these variables point to the beginning of their lists. All right? Then, after we create those 2 variables, we need to create a temporary array. That is the length of both of our lists put together. Our left half and our right half put together. So this guy's going to be empty initially. So here's our merge step. So create a pointer to the beginning of each half. So 2 variables. Create a temp array that is capable of holding a number of values equal to the size of the, well, let's say the length of the left list plus the length of the right list. Okay? Not the length of the entire array. Because at any point in time, in any version of our merge sort, we're only looking at a portion of that array. We're probably passing the entire array around because we're going to pass arrays by address, right? We always are pointing to the same address in memory. But we're going to pass some variables around, some integers that tell us which part of that array we're looking at. We're looking at the left half. We're looking at bucket 0 to bucket 4. We're looking at the right half. We're looking at bucket 5 to bucket 9, something like that. Okay, so we're going to keep track of which aspect of the list this particular call of merge sort is looking at. All right, so that's information we'll have to keep track of. Right now, we're just doing this visually. Okay, so right now, we're only looking at this part of the list, which happens to be bucket 0 and bucket 1. So we're going to create a brand new array that's the same exact size as the length of the left half plus the length of the right half. So 1 plus 1 is 2, so we have a 2-bucket array. Make sense? Next. While at least one of the begin variables points to a legal position in its respective array, we will continue to merge. Merge means, well, here, let's say to merge, we compare the value at left begin to the value at right begin and store the smaller in our temp array. Make sense? So let's do this visually. I'll let you catch up writing the words down real quick. So, we have left begin, we have right begin. Is it true that at least one of these guys points to a real bucket in its respective lists? If it helps in this example, I can still separate the lists for us to visualize these lists being two separate lists. Okay? Realistically, they're still in the array where they used to be. We just have kept track that the left list is from bucket 0 to bucket 0. And the right list is from bucket 1 to bucket 1 for this particular example. But visually, we can say these are two separate lists that we need to merge together into one list. Okay? Now keep in mind, when we're doing this right now, don't try to think about the code aspect of it. Think about the algorithm that we're doing. We're just playing with pictures. All right? That's all we're doing here. Okay? The code's going to be hard enough as it is. You're not going to understand the concept if you try to think about the code now. That's why we draw the pictures. Okay? So we have two lists. We're going to merge them together. So, is it true that at least one of left begin or right begin points to a real value inside their respective lists? Yeah. In this case, both of them point to a real value. Okay? So, we're going to ask the question, should this value come before this value? We can ask, is this value less than this value? Let's just say that's the question we're asking. The answer is no. 1 is not less than 1. Therefore, we will declare this guy to be the winner, right begin. So we'll take right begin, which is a 1, and we're going to put it into the current position we're filling in our temp array. So we're probably going to need another variable here. Maybe just called pause. That's going to point to the current position in our temp array that we are filling next. So the very first time we're going to be filling bucket 0. And at bucket 0, we picked the winner, which was right begin. So after we dealt with this value, right begin increments. So it just went from a 1 to a 2. And 2 is off the end of this right list. Okay, it's now in a legal position. It's no longer pointing to a place on the right list. Okay, so we'll place that winner inside of our temp array at bucket pause, then we'll increment pause. Because the next value we're going to place is going to be at position 1 in our temp array. Now we loop back up. We ask the question, is at least one of left begin and right begin a legal position? Yes. But only one of them this time. Left begin points to a real value. Right begin does not. So we can ask, which should come first? Left begin or an illegal position? Winner by default is left begin, right? So we'll take that value, which happens to be a 1 in this case as well, so this wasn't a very interesting merge. We'll see an interesting one here in a minute. So we'll take that, we'll put it in there, increment left begin, increment pause. Now we actually know we're done because pause is now off the end of our temp array. So we know we've actually gone through both of our lists because pause was this temp array was built in terms of the length of these two lists. Okay? But since we're looping, as long as at least one of these guys points to the real place, is it true that either left begin or right begin points to a real value right now? They both point to illegal positions. So we're done. And that's this line right here. While at least one of the begin variables points to a legal position in its respective array, we will continue to merge. Okay? Now, why I say respective array, let me just paint a little picture here for you. Let's say our list looked like that. Even though I want us to visualize them as being two separate lists, they actually are still in the original array. So when I incremented left begin from here to here, it now actually points to the beginning of the right half, which is an illegal position respective to our left list. So it actually points to a legal position in the array, but it's in the illegal position because the left list only goes from here to here. So it's off the end of the left list. That makes sense? So we can't ask the question, is this variable off the end of the entire array? Is it equal to the array's length? Because at each time through, we're actually only just looking, we're interested in one little piece of our big array. We were still, every single time through, we're still passing this entire array around. We're just interested in portions of it. So in our little example we just did, we have this entire 10 bucket array, but we're only interested in the first 2 buckets. That makes sense? So right begin, actually when it incremented to an illegal position, points to bucket 2. Which actually is a real value in our array. But it's not a legal position in our current world view of our list. All right. So, split these back apart for right now to keep our visual there. Both of these are in illegal positions now, so we know we're done looping. Finally, when we look at temp down here, that's our temp array. Let me actually label that. Call that temp. Temp holds the values that we ultimately want to be in our original array. In this particular case, they just happen to all be the same values. This particular list was already sorted, but we didn't know that. We sorted it anyways with the merge step. So what we'll do is we're going to loop through every value in temp, filling back in our original array with the values in the right order. Okay? Now, this particular call to merge sort can end because we've called merge sort in the left half, we've called merge sort in the right half. They both ended up being one lists. Then we called the merge step, which does what we just did, which should produce in the original array those values in the correct order. So this call to merge sort is now done. Bounce back up. That's this guy, right? So this call to merge sort is done. And up in memory, this variable's been overwritten by a 1. This variable's been overwritten by a 1. And the reality is even though it looks the same, the one that went here was the one that actually used to be here because of how our algorithm worked. All right? But we'll see actual overwriting here in a second. So we just dealt with the left half of this guy. Now we need to call merge sort on the right half. Is this guy sorted? Yes, because he's the one list. What do we do when we're dealing with a one list? We're done. That call to merge sort's over. So now we've called merge sort on the left. We've called merge sort on the right. What do we do next? We merge. This is now the list that we're merging, which also happens to be sorted. But we're going to go with this. All right. So merge step says to do what? Create a pointer to the beginning of each half. Left begin was here. Right begin is here. Because our left list is this part. Our right list is this part. So we're still dealing with the left and right halves that we call merge sort on. Okay? Then we're going to create our temp array. The temp array needs to be an array that's big enough to hold all these values. So 3 buckets. So in this example, here's our temp array. Then we do our loop. Is left begin is at least one of left begin or right begin pointing to a legal position? It is. Which should come first? A 1 or a 3? That is, which should come first? The value that left begin points to or the value that right begin points to? A 1 or 3? 1 comes first. So remember, pause down here points to the beginning of temp, the position we're loading into temp. So we'll go ahead and copy this, the left half, at position left begin into temp at position pause. There's our 1. Increment temp, because the next time we're going to fill in bucket 1. Increment left begin, because that was our winner. Loop back around. Is at least one of these guys a legal position? It is. Which comes first, a 1 or a 3? 1. Write the 1. Increment pause. Oh, you see that artistic magic? That's a skill set. Yeah, seriously. All right, so we got the 1, increment pause, increment our winner up here, which was left begin. Loop back up. Is at least one of these guys a legal position?
Yeah.
It is. Which comes first? An illegal position or a 3?
Illegal.
Huh? The illegal position comes before a 3? Yeah, can't compare them, right? So which comes first? An illegal position or a 3? By default, the winner is the 3. All right. That's the only real value we have to work with, right? He's the only guy left. Okay, we're picking kickball teams, and there's only one dude left. He's the next pick. All right. So we'll do our 3. Increment pause. Increment right begin. Does it loop back up? Is at least one of these pointing to a real position? No. So we're done with that loop. Now we copy all these values back into their original position in the array, overwriting the values that are in there. So it just so happens it's still going to be a 1, 1, 3 in this case. All right, but we overrode it in memory, so we loop through every position of temp, copying the values over begin to end in the portion of the array we're looking at. Okay, so now this call to merge is done. Bounce back up. That guy's now finished. And that, would you agree this guy's currently sorted? We didn't have to change anything yet, but we did overwrite it with its own values. So that call's done. Now we make our call on the right half, which is also already sorted. All right. But we're going to have something that's not sorted shortly. Make our call on the right half. Is this guy sorted? No, because it's not a 1 list. Call merge sort on the left. Is this guy sorted? Yes, so we're done. Call merge sort on the right. Is this guy sorted? Yes, so we're done. Then merge these two. And we can see when we go through our merge step for those two, it's going to be the same order, right? So we could skip this iteration through that. We'll draw the picture on the ones that actually change stuff, okay? So we've done the merge step on this guy. We went through the whole rigmarole, starting with the left half and the right half, and ultimately copied the values back in, and we copied a 1 here and a 5 here. So now this call to merge sort is done, which was our call to the right half of the list at this level. So now we're back to this call to merge sort, okay? We'd already dealt with the left half. We just finished dealing with the right half. We know that the left half is sorted in and of itself, because that's what merge sort does. Merge sort sorts. We know that the right half is sorted within itself. In order to get the entire list sorted, this whole portion, we have to do our merge step. So copy that. Come into here. We're going to do our merge. Set left begin to the beginning of the left half of the list. Set right begin to the beginning of the right half of the list. Make sense? And if it helps, we can visually separate these guys so they look like 2 separate lists. Then we create our temp array, which should be the same size as both of these put together. Initially, this will be empty. All right. So we have our loop. While at least one of these variables is pointing to a legal position, we're going to do some comparisons. Is at least one of them pointing to a legal position? Yes. Which should come first? A 1 or a 1? Okay, so is this guy less than this guy? No. So we're going to declare this guy to be the winner. Copy the 1 at position pause. Increment pause. Increment our winner. Loop back up. Is at least one of these guys pointing to a legal position? Yep. Which should come first? Well, is a 1 less than a 5? Yes. So we're going to take this 1, put it at position pause, increment pause, increment our winner. Loop back up. Is at least one of these guys at a legal position? Yes. Is a 1 less than a 5? Yes. Copy the 1. Increment pause. Increment our winner. Loop back up. Is at least one of these guys at a legal position? Yes. Is a 3 less than a 5? Yes. Copy the 3. Increment pause. Increment our winner. Is at least one of the, loop back up, is at least one of these guys in a legal position? Yep. Which should come first? An illegal position or a 5? By default, 5 is the winner. Put 5 in there. Increment pause. Increment the winner. Loop back up. Is at least one of these guys in a legal position? No. So we're done. Final step is to copy all this stuff back into our list. So that's 1, 1, 1. And we're okay overwriting the 3 because we still have a preserve down here. So 1, 1, 1, 3, 5. Now keep in mind that we were editing the actual array in memory. So by changing it there, we changed it here. We also changed it here. Because we overwrote the original memory address. Okay? We just, go ahead.
What's that step inside of our merge algorithm on the slide? The actual definition slide, yeah.
To merge, oh, okay. I understand what you're saying. We need one more tab. Oh, shift tab. There we go. Copy the contents of temp into the portion of the array we are currently looking at, overwriting any values in the original array. Temp holds them in order. We have them in order inside of temp. Now we're just going to copy them. We're just going to overwrite the contents of the original array in those particular buckets. Okay? So now we're back to here. Would you agree after we've done the 2 calls to merge sort and our merge step, now as a human being looking at this, is this list sorted? Yeah. So we know after we've called merge step, merge sort on the left, merge sort on the right, and ultimately merged, we know that now the portion of the list we're working with is sorted. So this call to merge sort is done. Now we make our second original call to merge sort. So now we're back to calling merge sort on the right half of the original list. So we dealt with the left half in its entirety before we ever started working on the right half. See how this works? We called merge sort on the left, then 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 we called merge sort on the right, then we called merge sort, well, then we called merge, then we called merge sort on the right, then we called merge, then we called merge sort on the right, then we called merge. Now we're calling merge sort on the right. See how the order goes? Okay, so now we just called merge sort on this. Is this the one list?
Go.
It's not. So this is back to this algorithm. Is the current list sorted? So we put in parentheses. is it the one list? Okay, the answer is no. So what do? We split the list in half. So we're going to call merge sort. Oh, sorry. Call merge sort on the left. Is this guy sorted? Nope, not the one list. We'll call merge sort on the left. Is this guy sorted? Nope, it's not the one list. We'll call merge sort on the left. Is this guy sorted? Yes. So we're done. Call merge sort on the right. Is this guy sorted? Yes. What do we do when we're back to this point? We call merge sort on the left. We call merge sort on the right. Now we do the merge step. So when we do the merge step for this one, we'll go ahead and do it since they are different values. And we'll skip a couple of the other ones to expedite things. So here's the portion of the array we're interested in. That's where left begin is. That's where right begin is. Okay? And actually, this is true to life. Notice that the portion of the array that I'm interested in this particular case, is buckets 5 through 6. Okay? So even though we're looking at a 2 list here that we need to do the merge on, it's only a portion of our original list, but it happens to be the real bucket 5 and the real bucket 6. So any changes we make here will have a global effect on bucket 5 and bucket 6. Okay? So we set those variables up. Create our temp array, which is going to be the same size as the portion of the list we're interested in. Set pause equal to the beginning of that list, not necessarily at 0. Pause will be at 5. Tell me why I'm wrong. See if you're paying attention.
Because the temp array only has the same amount of buckets as left begin plus right begin.
Very good. Temp array is a 2-bucket array. Bucket 0, bucket 1. So it just so happens that bucket 0 relates to bucket 5 here. Bucket 1 relates to bucket 6. So when we do that step where we copy it back in, we need to go through and copy it into the correct portions of our original array. That is, whatever's at bucket 0 goes in at bucket 5 here. Whatever's at bucket 1 goes in at bucket 6. Otherwise, we'll be overwriting other portions of our array over here that we're just playing with fire at that point, right? We're creating new values and adding them into our array. So we create temp. Temp is its own array that's, in this case, 2 buckets, 0 and 1. Start our loop. While these guys are the same, while these guys, at least one of these guys points to a legal position, which it does, is a 9 less than a 4? No. So we'll set 4 as the winner. Increment pause. Increment right begin. Loop back up. Is at least one of these guys pointing to a legal place? Yes. Does a 9 come before an illegal position? Yes, it does. By default, a 9 will win. So we'll put the 9 there. Increment pause. Increment our winner. Okay, so notice with this, I made it point to this list. So it's pointing to a real place in the array. It just happens to not be a legal place in the left half of my list. Does that make sense? Okay, so.
How will we make it know that though?
Well, if we know that we have a 2 list here, and we know the left half is 1 bucket big, and we know the right half is 1 bucket big, we know the begin and end of the left half is 5. So as soon as left begin becomes bigger than 5, it's illegal. We know the right half starts at 6 and ends at 6. So once right begin is bigger than 6, it's illegal. Okay? Even though it points to a real number that actually in our case here points to a real place in the array, it's illegal because it's not pointing within a place of the array that we are currently caring about. Okay? So this is part of what makes merge sort difficult. The actual algorithm for merge sort is quite simple. I mean, we're starting to see this repetitive nature of it. Okay? The hard part is just keeping track of a couple of numbers, making sure we don't overwrite the wrong parts of the array. That's why these pictures are important. Okay? So now, we're done looping. Our next job is to copy the contents of temp back into the portion of the array that we're interested in. Okay, so we're going to loop through every bucket of temp, but we're also going to keep track of begin to end of our array up here. So we're going to copy bucket 0 of temp into bucket 5 of the original. Copy bucket 1 of temp into bucket 6 of the original. Now that had a global effect. So that means this is a 4, this is a 9. This is a 4, this is a 9, this is a 4, this is a 9, this is a 4, this is a 9. And we didn't change it in a bunch of places, we changed it in one place, because we're looking at the same picture over and over again. This is bucket 5, 6, 7. This is bucket 5, 6, 7. This is bucket 5, 6, 7. Okay, we're just drawing these individual portions of that array. Okay? So by changing buckets 5 and 6 here, we permanently changed 5 and 6. 5 and 6. 5 and 6. All right, so we finished that merge step. So this is done. Now we're back to this list. We have a 2 list and a 1 list. So we just finished our call to the left-hand side of that list. Now we're going to call merge sort on the right-hand side. Still got to call it. We know we're going to come right back here in a second. There's the right-hand side of the list. Is this guy sorted? Yes, by definition, it's a 1 list. It's sorted. So we're done with that. So we called merge sort on the left. We called merge sort on the right. Now we'll do our merge step. What will our merge step produce here? 1, 4, 9. Correct? We've seen the merge step enough times. We kind of know what it's doing. Okay, it'll merge the left half and the right half together into one array. So this will produce a 1, a 4, and a 9. A 1, a 4, and a 9. A 1, a 4, and a 9. Now we're done with this call to merge sort. So we just finished our call to merge sort that dealt with the left-hand side of the list. Now we're going to deal with the right-hand side of the list. Call merge sort. Is this list sorted? Nope, not a 1 list. Call merge sort on the left. Is that guy sorted? Yes. Call merge sort on the right. Is that guy sorted? Yes. So we've called merge sort on the left. We called merge sort on the right. Now we do our merge step. Merge step's going to produce a 3 and a 5. Right? So overwrite 3 and 5, overwrite 3 and 5. Nothing really changed. So we just finished our call to the right half of this list. So we have the 3 list and the 2 list that we now need to merge together. And what's this going to produce for us? A 1, 3, 4, 5, 9? 1, 3, 4, 5, 9. Just finished that merge step. So now we bounce back up to the top. So this is a 1, 3, 4, 5, 9. So we just finished our original second call to merge sort. All right? So we have a 5 list and a 5 list. Would you agree that the first 5 list is sorted within itself? Would you agree that the second 5 list is sorted within itself? Yes. So if we go and do our merge step on this list, we'll just do it in place here. We're going to get a 1, 1, 1, 1, 3, 3, so 1, 1, 1, 3, 3, oh, 4 ones. We got 4 ones. 3, 3, 4, 5, 5, 9.
Yeah.
Like that. Copy the values back over. And there's our original array in the correct order. Easy, right? After we went through it a bunch of times, we start seeing the pattern. Okay? So let's write some code. Not all the code, because I'm going to give you some of it for homework. But not all of it for homework, just some of it for homework. Let's go ahead and actually create a let's create a new project for this. So I'm going to go to File, New, Java Project. And we'll call this CSC250 Fall 2014 Merge Sort. Click Finish. I have to give it some pretty descriptive names because you'll see I have multiple projects with sometimes the same name in here. All right. Very first thing, we're going to add a new class, and we'll call this guy driver. And we'll do our little hello world program just to make sure everything's kicking. Now, why doesn't this program work? Didn't have a main method. All programs begin and end with main. If you did not notice that, continue to memorize the hello world program. Public static void main string array args. Okay, now we get our nice little hello world program. We're going to go ahead and create a quick integer array that we can use for testing here. So we'll say int array AR is equal to, and let's actually use the values from our, actually it doesn't matter. So we'll say 3, 1, 5, 8, 13, 1, 0, 7, 12, 4. So this would be for a 10 list. Okay, but we're going to need to make sure it works for odd number lists as well. Okay, with an odd number list we had 11. Since in our example we always had the bigger list on the left half rather, we would have the 6 list and then the 5 list for our halves. Just so happened our example we had a 10 list, which would be a 5 and a 5 for the left and the right. Okay, So this is our original list of numbers. We'll go ahead and create our quick little display method for printing out all the numbers in an integer array. So we'll do static void display array. This guy will take an int array as a parameter. For int I is equal to 0. How many values are in AR? AR.length. I plus plus. And we'll print out whatever's that bucket I. Class method or instance method? How do you know? How do you call class methods? See, it's starting to sound chanty, isn't it? I warned you, didn't I? You guys didn't believe me. I can already tell. He's not even thinking about it anymore. It's like, it just goes into some sort of repetitive coma. All right. So we're going to call display array, passing an AR. It's going to go through the rigmarole here. It should display all these values, one per line. All right, so there's the values of our unsorted array. Now, we're going to write a method called merge sort. And merge sort is going to take in an integer array as a parameter. Okay, this guy is actually he's an abstract method for us. It's going to be a placeholder because we're actually going to call a secondary merge sort. But we want our users up here to be able to say driver.mergeSortAR, then driver.displayArrayAR. That's what we want them to have to do from an end user perspective. But remember, as we went through this, we knew that we had to keep track of the begin and end of our list. If we're dealing with only the left half, we knew the begin was at bucket 0, the end was at bucket 4. If we were dealing with the right half, the begin was at bucket 5, the end was at bucket 9. Make sense? So internally here, we're going to have to create some variables to keep track of where the begin and end of our list is, so that when we make our recursive calls, that particular copy of our merge sort helper that we're going to create here, that particular copy knows which part of the list it's interested in. Okay? So what's merge sort going to do? It's going to call another method. Static void merge sort, call this helper. And this guy's going to take an int array AR, an int begin, and an int end. That is, what's the position of the beginning of the portion of this array that I'm interested in? What's the position of the end of the portion of this array that I'm interested in? Okay? Now we need to make a decision here, and we need to stick to this decision as we're implementing this. Begin and end, what will they mean? Will begin be the index of the first legal position in the portion of the array? And will end be the position of the last legal index? Or will it be one bigger than the last legal index? Kind of like an array's length. The last legal bucket is the length minus 1. See what I'm getting at? Okay. There isn't a right answer here. We make a choice, but we have to then live with that choice and implement the rest of our code with that in mind. Okay? So, why don't we, for this example, have begin and end point to the real places? Okay? So begin is the actual first legal bucket in this particular list. End is the actual last legal bucket in this particular list. Okay? Inclusive. Begin and end, begin to end inclusive. So, what's merge sort going to do? The very first thing it's going to do is it's going to make the initial call to merge sort, which is going to be driver.mergeSortHelper. passing it our array, passing it 0 for the beginning, and what's the last legal bucket at AR?
AR.length minus 1.
Yep, AR dot length minus 1. Because we just decided that end will be the actual last legal bucket. So we passed it the position of the actual last legal bucket in the array. So this gets the ball rolling. All right? So this is a little convenience method that we wrote that abstracts this kind of ugly looking method call from our end user. Our end user is able to just call merge sort, and they go upon their happy way, when under the hood, this is actually calling our merge sort helper, passing it these weird indexes. That makes sense? We don't want to rely on our end user to have to put these in and know what begin and end mean. Kind of make sense? We certainly could have done it so our end user had to do it since we are the end user, but this is kind of a, an example of something you might do as a programmer. We probably aren't going to remember a year from now whether we chose n to be the last legal bucket or 1 past the last legal bucket. So if we take care of writing it now the correct way, we don't have to rely on our user remembering later. Okay? So now we're to basically what we've been calling merge sort, this guy. Go back to our algorithm. Merge sort says, is the current list sorted? How would we know that the current list is sorted? If it's a 1 list. How do we ask the question? Is the current list a 1 list? If what length's 1?
Length of the integer.
AR? The whole array? I'm just going to keep passing the same array throughout here. But I'm just going to say, focus on only the portion of that array that's begin to end. So AR.length in this particular example is always going to be 10. End minus begin? Okay. So in this particular example, begin was a 0, end should be a 9. So are you starting to see the evidence of what I said before? It's the whole complexity of this problem is keeping these numbers straight. Do we? If begin always points to the first legal bucket and end always points to the last legal bucket, how do we know that it's a 1 list?
If that equals 1.
If what equals 1? That!
No, what you're talking about, like between beginning and end, if it's 1, then
I'm going to say it again. I'll say it slowly so you guys can process. By the way, this is common. Because this problem is intimidating, right? Because it seems super complex. When you see the final code, how short this program is funny. Okay, it's not because of recursion. Typically, recursive programs are very short. So, begin is the position of the first legal place in the portion of the array we're interested in. End is the position of the last legal place in the portion of the array we're interested in. Begin and end are the same. If begin is equivalent to end, it's a 1 list. Right? Okay, and what do we do if it's a 1 list? We're done. So we actually only want to do crap if it's not a 1 list. So if begin is not equal to end is when we're going to do something. And what do? Call merge sort. Call merge sort helper on the left half. Call merge sort helper on the right half. Merge the halves. Those are the 3 things we're going to do. So if we're not dealing with the 1 list, we need to come up with what's the left half, what's the right half. Okay? So, we're going to have an integer begin left, an integer end left, an integer begin right, an integer end right. We need to set these guys up so that they are the correct values. Any time that we're dealing with this particular call, since begin and end point to the real places, the beginning of the left half will always be equal to begin. Right? The left half is going to be the left side of the part of the array we're interested in, which is the same left as we currently have. So if I'm looking at this array, 0 to 9 for our original call, not the one list. If I want to get only the left half, left begin is the same thing as begin was, which in this case was 0. If we had called it on the second half, where we sent begin as 5, end as 9, left begin as 5. Correct? All right, so the left begin will always be 5. What we'll do next time is we're going to have to figure out, how do we get end left? How do we get begin right? Well, chances are begin right will always be end left plus 1. End right will always be end. So we got to be pretty careful about end left. Is it begin, or is it end minus begin divided by 2? Might see some interesting examples. What if we took 9 divided by 5? Or 9 minus 5 is 4. 4 divided by 2 is 2. Is that the is bucket 2 in this example right here? If we're looking at this half of the list, is 9 minus 5, which is 4, divided by 2? Is that the end of our left half? Or actually, is that the end of our left half? We need to get a 7 out of it, right? Kind of see where we're going here? It's all about playing with those numbers and getting the math right. All right, so no homework assignment for Tuesday, but we will very, very, very likely have a quiz dealing with merge sort on Tuesday. So go back, watch the video, make sure you understand this algorithm. For instance, I might give you a list and tell you to show me the first 4 calls to merge sort. First 4 calls to merge sort that occur. And you should know that it'll be the left half, then the left half, then the left half, then the left half. Make sense? Understand how the recursion gets called. All right, so I will see everybody on Tuesday.